All right, so for the first couple of days, we're going to be looking at just basic ideas regarding chemistry. Chemistry, obviously, I got my PhD in chemistry. Does anybody know the origin of chemistry, where the term chemistry even came from? Think back to the Middle Ages. Anybody know? I'll give you a hint. In the Middle Ages, oftentimes people were really obsessed with mixing potions in an attempt to make what? Gold, right? What's that called? Alchemy, right? So really the origin of chemistry was alchemy. Alchemy has gradually progressed into chemistry. And it makes sense, right? It's got chem in both of these. Alchemy obviously didn't work out too well for those people working on it. Alchemy, the whole idea was creating new matter, or new elements even from other elements. You can kind of do that, and we'll talk about that in more detail, but it's really, really hard to make gold that way, and it's not something anybody would do. Chemistry has evolved since then. The founder of modern chemistry is this guy named Robert Boyle. And he had a book that came out in 1661. And I actually found a cover of the book on Wikipedia. And the thing I thought was kind of funny is if you look at the title here, they call it Alchemists. So it was still in this transition period where they weren't quite sure how to define chemistry. But Robert Boyle was the first person to kind of narrow it down into its own field and get away from the mystic side of chemistry. And really what he said was that matter is made of atoms or clusters of atoms and they are in motion. We'll talk a lot more about what an atom is, but does anybody know just from general day-to-day life? What do you think?
It's the elementary building block. It's a small protons and neutrons. Protons and neutrons in nucleus with electrons going around it.
Yeah, you're way ahead. So atoms really are the smallest individual particle we have, right? So imagine you cut something once, split it into two pieces, right? Do that over and over and over and over and over again until you get down to the smallest piece that you can't cut anymore. That's essentially an atom. We'll talk more about that. Obviously, in science, there's a huge amount of exceptions to rules, and we'll talk more about those too. So there are some atoms you can split. Does anybody know an example of that? What do you think? Hydrogen? Not easily. You would have to do that in a particle accelerator. I'll give you an idea. Think of a bomb. Anybody know? Atomic bomb, right? So in World War II, we dropped atomic bombs. Those were uranium and plutonium. So some atoms you can split, and when you do that, it releases an enormous amount of energy. One of the reasons I really like chemistry is it's this branchway to a million different fields. So I like to show this to show the broad diversity. Chemistry is obviously associated with medicine, so things like toxicology, pharmacy, neurology, biochemistry, and so on. It's also related to earth science fields like geology, paleontology, stuff like that. It's related to physics, electronics. We also have things like meteorology, metallurgy, engineering, archaeology, ecology, agriculture, botany, biology, all of this stuff. My favorite quote that my professor told me when I took chemistry is biology is really chemistry, chemistry is really physics, and physics is really math. So really we're at this big continuum of various sciences. They branch, they cross over. We can't really define chemistry as one thing because it crosses over into so many different fields. That's why I love working on this. So like I said, I started out as a biologist. All of a sudden I became a chemist. And at the end of grad school, I was actually working on a project related to agriculture. So you never know where this wacky field will take you. All right, we've got one other big thing we have to talk about before we get too far into science, and that's the scientific method. Has anybody heard of the scientific method? A little bit. It's one of these things where it seems pretty elementary, but for a long time it wasn't well practiced. So I'll walk you through the modern scientific method, and I'm going to boil it down into what I view as the most important parts. So the first thing I always do is I always think of a question. Or actually, before that, I make an observation, I guess. So maybe I make an observation in my yard that my rose bushes in one corner of the yard are growing really, really, really well. And then, based off of that, I develop a question. So for example, I could say, all right, I made an observation that the rose bushes in one corner of my yard are growing really, really well. Question is, well, why? Why are they growing well in that side of the yard and not in the other side of the yard? And then after this, I have to make something called a hypothesis. Does anybody know what a hypothesis is? A hypothesis is really some sort of testable explanation as to why you think something might be occurring. So for example, I could say, my hypothesis is that the rose bushes are growing well in that corner of the yard because they're getting more sunlight than the roses in the shade, right? How could I test that? Anybody know? What do you think?
You could grow 2 different rose bushes, one in constant sunlight, one in constant shade.
Exactly. So with rose bushes, I could say, all right, maybe I do an experiment where I have one set of rose bushes growing in the sun, another one in complete shade, and then I test it, right? And that's exactly the next part. You want a testable prediction. The other thing you want to do after this is not just come up with a testable prediction, you actually want to test it, right? So we'll say gather data and test your prediction. That's really important. The other thing too is sometimes we gather data, we test our prediction, and it does not match at all what we predicted. So maybe the sunlight didn't do anything. The bushes grew about the same. What would I do then? What would you guys do? Would you just give up, go home, dig up your rose bushes, throw them away? Yeah, maybe develop a new hypothesis. So for example, what you can do is refine alter, expand, or reject your hypothesis. I guess I need that. And then make a new testable prediction, and you can get stuck in this feedback loop for quite a while. Oftentimes, this is what differentiates good scientists from bad scientists, is they're willing to get stuck in a loop over and over and over again and be willing to fail over and over and over again. It can be an incredibly frustrating process, but the whole idea is that you go through this loop over and over and eventually keep on changing your hypothesis until you get a better testable prediction, right? And then once you've done this and you've got a really good amount of data, you've tested your prediction a lot, you now have some basic understanding of what's going on, then we go ahead and we develop a theory. So theories are essentially the last step of all of this. Does anybody know what a theory is? It's basically an explanation of what you think happened based on all the data that you gathered, right? So once you've collected enough data, you've got a lot of evidence maybe supporting some explanation that you're coming up with. So it's important to eventually land at developing a theory. Does that make sense? Okay, so let's go ahead and define some of these in a bit more detail because I did throw out a lot of new terminology. So the first one was hypothesis. Like I said, a hypothesis is essentially an educated, testable guess. And I'm going to put guess in quotes because a lot of scientists don't like guessing because it really is an educated opinion about something, about an observation. The key word here is educated, right? So like with my rosebush example, I knew a little bit about plants needing sunlight, so I was trying to take that educated opinion and use it in this situation. You don't want to go off the deep end with your hypothesis, right? So with the rose bushes, you wouldn't say, oh, my rose bush is growing well because I had a good dream last night about roses, right? That's maybe not the best educated guess. All right, next one was theory. And like I said, theory is kind of the end point for the scientific method. So a theory is an explanation supported by data. The key word here is explanation, right? I don't like the way a lot of people use the word theory in day-to-day life. They'll say, well, that's just a theory. Like, well, that's like saying you're only supporting that with evidence. It's like, well, yeah. A theory isn't a theory if you have data that refutes it, right? As soon as you have data that refutes your theory, it's no longer a theory. You have to start over again in the scientific method. So a theory is something that's incredibly strong, right? Because as soon as you find something that breaks it, you have to start all over again. All right, next term is law. And this isn't like judicial law in the US, this is scientific law. And this is a little bit different than theories, so I will explain the difference. It's a summary of a large body of info but provides no explanation. So really the difference between a theory and a law is a theory explains the why, a law doesn't, right? The way I often remember the difference between these is laws oftentimes have formulas associated with them, right? So for example, is anybody familiar with Newton's laws? So Newton was one of the first physicists to provide a huge amount of laws for the basis of physics. And all of his laws can be supported with a mathematical equation. It doesn't explain why it happens, it just says we observe this, and it fits a math formula, right? It doesn't explain the why. A theory, on the other hand, might be something like the theory of evolution, where it says certain species exist due to a process of natural selection, and you'll learn more about that if you go on and take biology classes. So they are different, right? Theory is the why, laws just explain something without the why. Are there any questions with this? Nope. All right, we've got a few more things. We may not be able to finish this today, but I figured we'd get a jump start. And this is critical thinking in science. And the textbook has a nice acronym that they use called FLAIRS. So it's capital F, capital L, lowercase a, capital R, capital E, capital S. So the first one is F, that's falsifiability. And basically what that means is that your testable prediction has to have some way of being wrong, right? If you have a prediction that is always going to be proved right, that's not a very good prediction. So falsifiability fits in there. So there must be a conceivable way to prove your claim false. Seems pretty simple. Next one is logic. You must use logical reasoning. Essentially, that means get away from the mystic side. Like I said with my roses, me dreaming about roses doesn't really follow much logic as to the roses' growth patterns. Next one's really important. This is actually a big problem lately in science, is reproducibility. And essentially that means data must be able to be replicated. This is a big deal, especially in some science fields like psychology. For example, there's been a lot of psychology papers that have been published recently where they haven't been able to produce the data reliably. That's a bigger problem with science, this pressure to constantly publish because your job's on the line. We have to make sure that our data is reproducible, and we have to make sure that people actually go out and test your data to make sure it's reproducible. If everybody takes it at face value, then science kind of breaks down, right? So we have to be able to reproduce it. And then the last one is sufficiency. I apologize if my handwriting's not the best. Essentially what this means is that there's a burden of proof. All right, another way of thinking about this is extraordinary claims require extraordinary evidence. So those 2 points are really key, right? If you're trying to come up with a theory, the burden of proof is on you, right? You need to provide an overwhelming amount of data. If all you do is one experiment, it's probably not enough. You need to do it over and over again, test it in a variety of circumstances, and make sure that when you go out into the public and present your theory, that you're presenting something that's strong. Scientists don't like being humiliated, right? Second thing, like I said, is if you're making a really extraordinary claim, that means you need even more evidence to back up your claim, right? You can't go out there and say something wacky without having evidence to back it up. So that's 2 key points. The last 2 are pretty important too. This is correlation does not equal causation. And I'll show you an example of this. I really like this one. Somebody charted organic food sales and then charted the rates of autism in the general public. And if you look at this, you'd say, hey, it's a pretty good match. Organic foods cause autism, right? Does that make sense? No, just because you have 2 trends that happen to overlap doesn't mean that they're at all related to one another, right? You can actually do a lot of these funny things in Google and match up like deaths per capita by like, I'm trying to remember, it's deaths per capita by like number of kids in 3rd grade or something like that. Just wacky stuff that doesn't make any sense. It doesn't mean that they're causing an effect, right? Obviously, there's a more popular one with autism. Does anybody know what that one is? What is that?
Vaccination.
Vaccination, right? So vaccination is a classic example of correlation not being causation. They've studied that like no other branch of medicine. They've put a lot of time into money showing that there is no causation there. It's just happens to be rates of autism are going up and we don't really understand why. All right, the last one is authority does not equal evidence. So just because you're really famous or because you've got a fancy title doesn't mean that you're more important than anybody else in science, right? That's really important here. A good example of this, I think I've got 1 minute, is Linus Pauling. Linus Pauling won two Nobel Prizes, one in chemistry and a Nobel Peace Prize. And he came out and he said that DNA, the genetic code inside our body, was some structure that I think was a triple helix or something like that. He basically was all wrong. But everybody was like, well, I mean, he won 2 Nobel Prizes. I don't want to refute him. We have to do that in science. We have to be willing to stand up to authority and go gather data on our own to refute other people's ideas. All right, so that's where we'll end today. If you have any questions, I'll hang out here for a minute too.